Welcome to our Modern Pump Selection for System Efficiency seminar. This is a new seminar that Pleasance Company is doing because we feel like that in the modern world, we should maybe begin to look at pump selections and pump applications differently than we have in the past. The punchline is that we no longer run pumps at a constant flow and constant head. It's okay to look at beep, which we'll talk about in more details, but in reality, we're moving around on the pump curves. So we kind of want to look at efficiency islands or efficiency areas and have the biggest efficiency islands as we can, realizing that our actual pumps are moving back and forth and they're not at any one specific efficiency. So it becomes the average efficiency over the range of the pump that we're interested in. So we got to go back to basics, and we do like teaching basics, and we're going to talk about pump laws real quick. We're going to talk about a little bit about pump head loss calculations, which is critical to this. Then we got to teach a little bit about pump curve review and how pump curves interact with the system curve. System curve reviews a little bit, a couple of examples, and try to summarize this a little bit because this is a seminar that's going to start teaching some new things to you, and you're going to need these for the next generation, for the modern world. So look a little bit real quick at pump efficiency laws, and for the purpose of this seminar, we want to look at the pump end. We do have motor efficiency, we do have variable speed drive efficiencies, and all those that have to be dealt with in the real world. But we want to look for this seminar and try to understand the pump end, the pump efficiency. This little equation kind of gives you that thought process. In other words, we got brake horsepower going to turn that pump around, but the water horsepower is what we're after. That's what gives us cooling or heating or the process that we're in. In this particular case, the water horsepower efficiency is 81 points. We want to look at the efficiency of the pump end and deal with that today, and this is why we have this particular slide here. Now, so you're talking about brake horsepower. Now, brake horsepower would be the horsepower required to get you that pumping, and that would be where your real KW is or your cost is. And we want to kind of realize that brake horsepower is money. It's a sack of money. It's a bag of money. And we like to minimize that brake horsepower as much as we can to keep the electric bill as low as we can. So if we start looking at the pumping piece of that, it's gallons per minute times the head. Now, water-wise, specific gravity is 1, and so to keep it simple, let's just look at water for the time being. And you see the things that are varying in there would be that pump efficiency as I move around on the pump curve, which we want to talk about, and the gallons per minute and the head. And the real world we're in today is two-way valves. It's variable volume pumping. So that GPM is going to be changing. It's not going to be constant. So when we go to select a pump, we need to keep in mind some kind of a load profile or some kind of way to recognize the fact that that GPM is changing, and that can impact the horsepower, or it will impact our bag of money, which is the electric bill each month. So here's the brake horsepower formula made real simple for water. And as you can see, we took out specific gravity because we're going to call it 1. So we got pump efficiency in it, which we can play with a little bit, and GPM and head. And we want to look at that water brake horsepower so we know what's happening. So we got to look at pump efficiency laws a little bit. And this is a review, but you need to basically go back and understand this from scratch if you're going to apply pumps properly. Because now we're dealing with variable speed drives. Now we're dealing with flows that vary. So let's look at speed changes and how they relate to pumps to begin with. In other words, the flow in GPM is directly proportional to the speed change. If I change the speed, then the flow is directly proportional to that. If I change the speed, my head is directly proportional to the square. In other words, if I double the speed, my head's going to go up 4 times. Last but not least is that brake horsepower, that money bag, that KW, that your electric bill varies as the cube. In other words, if I cut the speed in half, my horsepower becomes 1/2 times 1/2 or 1 times 1/2 or 1/8 in theory. 1/8 in theory would be the brake horsepower if I were to cut the speed in half. My flow would be half and my head would be 25%. Now what's neat about this little speed change thing, take a look at what happens when I look at impeller sizes. And the point here is to try to make you understand that statement in ASHRAE 90.1 2010 that you can either vary the speed of the pump or cut the impeller, because either one of them does the same thing. So let's play around with impeller diameters and see how that applies to speed. In other words, The ratio of the impeller diameter controls the flow rate just like the ratio of the speed. It's directly proportional. The impeller diameter squared controls the head, and the impeller diameter cubed controls the brake horsepower. In other words, I can trim a pump impeller, or I can vary the pump speed and do the same thing. So a lot of people say that a variable speed drive is really a pump impeller trimmer. And they kind of look at it that way, because if you look at the laws, hopefully you recognize you're getting the same result. So let's just kind of keep these fundamental things in line and see where we're going. All I've done here now is I've taken those laws, the theoretical laws of pumps, and put them on a little chart, and we're going to take a couple of minutes because I want you to understand this. This is kind of what the variable speed drive people are preaching to you that don't fully understand systems. And the problem is, this is theoretical. Let's review the theoretical thing again. Let's assume we're at half speed. Remember the previous slide showing the basics. Let's just go to half speed. So at half speed, I would have half flow. I would have 50% flow. So you see the 50% speed line, and you see the 50% flow line. My head at 50% flow, 50% speed, would be 25% to switch it to the left axis. The vertical axis on the left is head. The horizontal axis on the bottom is flow, and the vertical axis on the right is horsepower. So the last thing, the horsepower varied as the Q, remember? So at half flow, we have half speed, 25% head. Wow, 12.5% brake horsepower, 1/8. That's the theory. And this is what makes variable speed drives so attractive and so powerful on a centrifugal pump. But here's the problem. We have people applying this. We have variable speed drive people applying this. We have pump people who believe this happens in all cases, and it does not, because we have assumed here 100% variable head. This is where you got to begin to think in terms of the future. Why are we not getting this much savings at half speed on most jobs? How come most jobs at half speed are not half flow and are not 12.5% brake horsepower, even though theoretically that says what you should have? This is the essence of this whole seminar, is get you to understand theoretical is great. How do you break into this and get the real world? What really happens with a variable speed pump? We got to back up a little bit and keep taking some basic fundamental pieces here. So let's go to ASHRAE 90.1 2010, and by the way, it's in 90.1 2013 just as well, and look at pump head loss calculations. So here's the standard 90.1. You guys have seen it. This is 2010, and 2013 says basically the same thing on pump head loss calculations. What I find interesting is that obviously DOE has adopted this, and this is 2010, and they said by October the 18th, 2013, all states should have an energy building code equal to or better than 2010. Here's 2013. Yeah, 90.1. 2013 is now out and approved. DOE looked at it and ruled, you can read the bottom red line, that by September the 26th, 2016, all states should have an energy code equal to or better than standard 90.1 2013. By the way, 2016 has been worked on right now. This is not going to stop. It's going to keep coming. So where are we? Here's my little chart, and the last update I had on it was June of 2015, so it could be some slight changes since then. You can go online to the website and you can dig this out. But notice North Carolina, where I'm in Greensboro, North Carolina today, and I travel a lot, but just looking at North Carolina today, it's a blue state, it's 90.1 2010. If I look a little bit at where Maryland up there is green, Vermont is green, and green, by the way, is 90.1 2013. So now you can see the status of the various states between 10 and 13, and the point to make here is states are getting there slowly, but they're coming. Energy codes are getting stronger, so I think it'd be fair to say that roughly half of the states now are 2010 or higher in energy codes, and it's just going to build every day. So we can't ignore this. We have to understand that. So let's take a look at 2010, which is in 2013 also, and look at pump head loss calculations. We're talking about pumps today. Why would ASHRAE ask you to do a detailed pump head loss calculation? Why would they go to that trouble? And you can read the red statement down there, and it says the pressure drop. through each device and pipe segment in the critical circuit at design conditions shall be calculated. So ASHRAE energy code is saying to you, slow down and do a detailed pump head loss calculation. Here it is, right out of the standard, which is energy code, and this is something we're going to have to do. Now, there's all kinds of tools out there to help you with. And here's one that's a little app on iPhone or on iPad that's freebie to you. It's easy to get a hold of. All you got to do is simply go online and search for the app, and it will size pipe for you. I use it every single day. This particular one is the Ballinghaus System Sizer. There are other ones out there, but this is a great one. It's a freebie. It's a design tool. It's not a product. Basically, it has lots of pipe sizes in it. It has PVC pipe. It has English and metric. In other words, you can calculate in English and switch the metric back and forth very easily. Handles fluids other than water, and I think it's a little application that I use every single day. You should go get it. It's a freebie. There's also a Windows-based version of the System Sizer that's available to you that you can switch back and forth between Spanish and English and the other things we talked about. Plus it supports ASHRAE 90.1. And this is the piece I want to get to. Again, a design tool, not a product, free. Go online, download it, use it. It's a great little tool. Here's where it comes into play with 90.1. One of the screens, and you can see the shot here, has elbows, T's, gate valves, butterfly valves, place at the bottom for your chiller, your heat exchanger. What's neat about this, you can plug in K values, CB values, PSI values, feet, whatever, and it will convert all those pressure drops to the same set of units, whatever you pick. Put your number of feet of pipe you have in, how many T's and elbows got, and on the left-hand side, it will give you the total head loss. So you got a way to do what ASHRAE 90.1 2010 asks you to do. You have a way to calculate that actual head loss and get it in your file. You know, you make a PDF of it or whatever you want to do and you keep it. But this is a great tool. You're going to need a way to do it. I would strongly suggest you go get it. It's a freebie again, and you need some way to make sure you got the right pump head loss calculation. Now, why we're talking about all this again is we're basing all of this modern pump selection on the changes. So what is the change? Here's another piece of the code, the standard, and which has become building code. They want you to reduce the horsepower to 30% at 50% flow. They want to vary the flow. A little further down, they want you to change the differential set points on your critical zones to the minimum required to make sure at least one of those valve positions is nearly wide open. So ASHRAE's driving you to lower kW as you vary that flow. So they're saying to you, let's look at half flow. Let's look at half load. Don't just look at beep. Don't just look at 100%. Let's look at some kind of a load profile to see what the actual kW is going to be in the real world. And this is what's driving this whole discussion about modern pump. So we're going to ask you to slow down and look at something again. Here's a kind of a reference to ARI 550, which is the original IPLV load profile. For those of you guys who are not familiar with this, I don't have all day to play with this, just put it real simple. It was a standard that all chiller manufacturers through ARI agreed to take a standard load profile and look at kW on a chiller. To take a standard ARI-approved load profile and rate their chillers. Now, it won't apply to every chiller plant. It won't apply to every multiple chiller plant in particular, but the issue is it is a load profile that's standardized. So if you don't have a load profile, then this gives you a way to very easily reference various types of chillers at a load profile other than 100%. And the whole message of this is IPLV is at a set of numbers. The NPLV allowed you to plug in your load profile. In other words, if you don't want to use a standard IPLV load profile for loading up of your chiller, which we'll look at in just a couple of minutes, and you know your load profile, so much the better. Let's go to the NPLV and load it in there, and you actually have the load profile for your project. In absence of knowing that, here is the IPLV load profile. And the whole point I want to make to you is very simple. What percent of the time are they telling you you got 100% load on your chiller? 1%. 75% load, 42%. See the weighting column? half load, 45%, 25% load, 12%. What they're telling you is, why do we want to look at 100% load and just look at that all the time when it's only 1% of the time? We need to average this out to get the real kW per ton. So what we're suggesting to you is, why don't we take this approach and look at pumps? I can make a pretty good argument to you that as your load profile changes for hot water and or chill water with two-way valves, I make a pretty good argument to you that your flow rate in GPM is going to change. May not be direct, but it's going to change along with the same change in your load in BTUs, whether it's heating and or cooling. I'm going to suggest to you that we use this load profile when we look at pumps. You're not going to run a hot water pump wide open 100% of the time. You're not going to run a chill water pump wide open 100% of the time if you've got two-way valves that the code demands. So we're making a statement to you, we need to start looking at something other than just beep efficiency. We need to be looking at efficiencies with some kind of a standardized load profile. If you know your actual load profile, great, let's use it. But if you don't, let's have a standard that everybody can use. And this is already out there, already ARI approved, everybody understands. Even some of the other people demand minimum IPLV numbers, kW per ton. We're walking down the road of saying maybe, just maybe, we should be looking at some kind of an IPLV pump efficiency. Yes, some kind of an IPLV pump efficiency so we can begin to look at the real world. So let's look at pump head loss calculations a little bit, kind of get in your mind something called constant, fixed, and variable head. Wow, some new terms for you maybe. Let's take a look at a typical little closed system. It doesn't matter whether it's heating or cooling. I just want to look at the two-way pump varying the flow through the two-way valves. I'm not worried about the chiller pump right now. Just look at the pump circulating through that reverse return set of piping. And I'm going to ask you a simple question. You ever thought what pieces of head in that pump would be variable and what part of that head would be constant or fixed to give you the total head? And I want you to slow down and stop and think for just a second. The only thing that's going to change the pump speed really is the variable head. In other words, here's a very good statement for you. Where I have friction or variable head, if I double the flow, my friction goes up 4 times. If I cut my flow in half, the friction becomes 25%. It's back to that square thing we talked about. So that's the only thing really changing the pump speed in overall pump head loss calculation is the piece of the pump head that's variable, that's changeable with flow. Now there's a constant piece there, which is that minimum differential control head that I need across the two-way valve and the cooling coil and the balancing valve to make sure that that particular zone has 100% cooling available to it if it's needed. It may not always be needed, but it's got to be there so when that customer or that critical zone comes in and wants 100% cooling or 100% heating, and they go to the T-stat opening it up, you've got to have a differential head there right now. You can't wait. It's got to be there waiting on you to give you full cooling or full heating through that zone at that particular time. There's a minimum pump RPM required to give you that minimum head, because that's not variable. That's fixed. That is the fixed head. That's the control head. We're going to talk about that a little bit longer in the next 2 or 3 slides to try to get your brain wrapped around this, because this is maybe a new request to you. So keep it simple. On this particular slide, the red part of the piping is the variable head. The green is the constant head. So if you look at it a little bit further, here's all the numbers, and don't get caught up in the numbers. I'm just trying to teach you how to do this. I want to calculate from now on my pump head always with what piece of that pump head is variable or friction, what piece is variable or friction in a closed system, and what piece is that constant fixed control head. Here are all the numbers. Let's color it up for you. Here's a reverse return system, again, the same system, and the one we just picked, 52 feet out of the 80 feet total pump head is variable. If I cut the flow in half, that's going to be 25%. That 28 feet constant is always there, even at zero flow. The constant head is always there, even at zero flow. And you got to run your pump fast enough to get that constant head, otherwise your people will not be happy. Where my numbers come from, here's a color-coded little slide you can spend your time and play with a little bit. But those in red are the variable heads. In green is the constant head, the control head, which we're going to look at a little bit deeper, don't worry. But basically, it's the head required across the two-way valve, the heating or cooling coil, and the balance device to give you 100% flow through that critical zone, wherever that critical zone may be. That's the number that's constant. We cannot get below that. So let's have a little bit further. Here's a direct return system, same concept. And again, you see the variable head is in red. In this case, the constant head, I believe, is orange. Constant fixed head, again, is where that differential pressure transducer is sensing, and it's sensing across the critical zones coil, the two-way valve, and the balancing device. That is the constant fixed control head that you've got to run at zero flow. You've got to run your pump fast enough to give you that head. So if that customer comes to that zone, wants cooling or heating right now, the pressure is there to give them the flow. Otherwise, they will not be happy. They're going to be complaining. That's kind of the concept. So let's see, where would you have 100% variable head? We just showed you where you probably would never have 100% variable head. So is it possible to get 100% variable head? Keep it real simple for you. If you got a two-way valve, no. If you got a two-way valve, you're always going to have some constant head across that valve, even at no flow, to make it available in that critical circuit to cool. Here's an example of a 100% variable head maybe. I got rid of the two-way valve. There's no two-way valve. Hard to find these applications. In fact, very seldom do you see them. This particular one is process. I got a variable speed pump with a heat exchanger. I'm running through a process and I'm sensing temperature. The temperature is directly controlling the speed of my pump or the flow of water to the process. So now I've got a 100% variable head. I've got one zone, no two-way valve. My temperature sensor is controlling the speed of the pump directly to vary the flow to maintain the temperature in that process at whatever it needs to be. So in this case, at half flow, I would have 25% of the head or 12.5% of the brake horsepower. In this case, I do have 100% variable head. It's very hard to find that. That's what the variable speed drive people were promising you on this first set of slides we looked at. That was at half flow, it'd be half speed, 25% head, 25% brake horsepower. That's the promise. But to find an application like this in the real world, it's extremely hard to find this in the real world unless you do away with the two-way valves. That may be where we're headed, but we're not there yet. So let's take what you've just learned and put it on a flow chart and see what it does to us as far as brake horsepower is concerned. I ask you to look at calculating variable head and constant head and add the two together. So what happens is you change the relationship in that total pump head of the percent variable and the percent constant. Here I have a little diagram for you. On the left-hand axis, vertical, is the horsepower. The bottom axis is the flow. And I got try to color code these individual lines so you can keep up with me. But what the variable speed drive people promised you, what the theory is, would be the bottom green line. The bottom green line is labeled 100% variable head, 0% constant. You can't find that application. It's very hard to do unless you don't have a two-way valve. And about everything we deal with has two-way valves for control. But take a look at 50% flow. Now remember, this is PowerPoint. The best I can get the numbers maybe off a touch, so forgive me. But at half flow on that green line, I'm at 12.5% brake horsepower. I'm at 1/8. That's what you got promised. But only if you have 100% variable head. Look what happens as I change the ratios a little bit. Let's stay with 50% flow. Let's stay with that number because 50% flow is going to be the vast majority of the time half load. Heating load, cooling load, half load, half flow. You're not going to be at 100% flow. Let's look at the real world. Let's look at where we live most of the time. That's going to be around that 50% flow or that 50% load number. Let's go back to my 50. 75% variable head, 25% constant. I'm in red. The best I can read it, 50% flow, 75% variable, red line I'm up to. Help me out a little bit. About 25% brake horsepower. So do you see what's happening as I change that ratio? Let's jump up to 50-50. Let's go to the blue line that says 50% variable head loss and 50% constant. 50% flow. Read it on up. The best I can look at it, we're about, 40% brake horsepower. Go all the way to the top straight line, which would be 100% constant head, 0% variable. That actually is a blue line there. look at the 50%. 50%, I'm up to what, 75% roughly horsepower. What's the message? As you increase the percent constant head, the brake horsepower is going to go up, even at zero flow. Look at zero flow. At zero flow, I'm still running pretty fast, and I'm using a lot of horsepower. Let's bring this over to another chart and try to make sure you understand what control head is, fixed head is. We're going to review all this again. Don't worry, I'm coming back to this one again. It's important. So pump curve review. How are we going to tie this to a pump curve? This is what we call best pump efficiency point, beep. Everybody in the industry calls this beep. Oh man, I'm proud of my pump. My pump's 86% efficiency, right at that little sweet spot. I'm going to pick my pump at that sweet spot, right where my little yellow area is, 86%. But the problem is, it only runs there maybe 1% of the time. The other 99% of the time is somewhere else. So we're so proud of ourselves that we picked at 86% beep, but we don't run there. What is the meaning of something to pick and we don't really use it? The real meaning would be to look at an efficiency island. How big an area in there do we have with a high efficiency? Where is the pump going to be moving with some kind of a low profile? And we're going to say two-way valves. We're going to say it's a low profile, and we're going to say as that low profile changes, I'm moving back and forth on that pump curve. Makes a little sense, I hope. So we want to look beyond beep. Beep's important. Didn't say it's not important. It is important. But we've got to look beyond beep. Here we go back to my efficiency curves with a variable speed drive. Anybody's pump. This is what happens, and you kind of got to begin to pull these pieces together. And we're going to be repeating this a lot. So if you didn't get it the first time, maybe you'll get it again. I'm at beep in this case at 85%. See my little yellow area at beep at 85% efficiency. See my speed lines going from 0 speed to 100%. On the left side is my head. So and the bottom is in GPM. So in this particular case at beep, which is probably what, 800 GPM, maybe at 110 feet ahead roughly, if I had 100% variable head, in theory, I would follow that 85% beep line all the way down to 0. Now we said we're probably not going to find a situation with 100% variable head. So as you change your speed in theory, 100% variable head, your pump just follows right down those lines. That's what everybody believes. Listen to me, that's where people are getting in trouble with this. They're saying to themselves, I just put a variable speed drive and fix everything. That's not true. Variable speed drives will not fix everything, and people are getting in trouble because they don't go any deeper in this. Let's go a little bit deeper. Let's ask you the question, what would happen if my minimum control head was 25 feet like this purple line? What happens to my beep efficiencies now? In other words, in the real world, as I slow the flow down and slow the speed down, I'm not following the 85% beep green line all the time. I'm following that purple line because at 0 flow, I've got to have 25 feet ahead. It looks to me like I'm going to need to be running at, what, about 45% plus speed? And I just crossed over the 50% efficiency line. I just crossed over the 50% efficiency line, and you thought you were at 85. If you promised your customer to stay at 85%, if you promised your customer that you would be down to 0 speed at 0 flow, you're in trouble because the real world is not going to let you go there. Let's go a little bit deeper with this concept. Let's look at minimum speeds, efficiency changes, and see what happens. So before we go too deep with that, let's go back to this constant fixed head and variable head thing and give you a couple of little pump curves, and I'll get them all up there so you can play with it. The black line on the bottom is that system curve. That would be the 100% variable head line. That would be where we'd like to be. We just said it's just about impossible to find an application like that. So what do we have to do? Well, above that, we have this control curve. That's a little orange line, and that's the one that crosses the pump curve. That's the one where the system curve is going to cross the pump curve. First law of thermo, energy in is energy out. That's the fixed head we got to look at. Make sure I don't lose you here. That orange line represents the minimum constant fixed head required across that two-way valve, coil, and balancing valve to make sure I've always got enough differential pressure at that coil to give 100% flow through the critical zone, wherever that may be. So that means back at 0 flow left-hand axis, I'm not at 0 head, I'm at that minimum control head. So that control head is critical. That control head is the fixed head. That's the head we got to deal with
That's the one that's going to control the minimum speed of my pump down at shutoff, and it's going to control the efficiencies. And we're saying to you, we got to start looking at that. We're misleading the clients when we say a variable speed drive will fix anything. We got to look at what really happens. So you kind of get that concept in line. Let's take a look at this control head, this fixed head. Let's play with it a little bit and see what it does to my minimum pump speeds. So here's the question. Here's a big question. What happens to the minimum pump speed as you increase the minimum control head or that differential pressure set point, or what we call the fixed head? It's all the same term. The graph we just showed you showing the control head is the key. Let's plot it on a curve here and see what happens to my minimum speed as I increase the control head, the fixed head, the percentage control. What happens? Here's a little plot, and I've got a pump pick for 70 feet ahead. Everybody see that? I got 100% speed. My total pump head is 70 feet. On this particular graph here, I'm looking at a control head of 30 feet or a fixed head of 30 feet. And you see my control head. The purple line is the system curve as we originally knew it. I got to add 30 feet to the purple line to give me the light blue line, which is the control curve. Here's the question. What is the minimum pump speed at zero flow? What is the minimum pump speed at zero flow? Let's just see. At zero flow, I've got to maintain 30 feet, not zero. You see, in 100% variable head, I can go to zero head at zero flow. I can't do that here. At zero flow, I've got to have 30 feet. So what pump speed do I need to give you to 30 feet? Roughly 60% pump speed would be the minimum speed of this pump at zero flow. Repeat that. The minimum speed of this pump at zero flow would be 60% to maintain that 30 feet, because that's the critical zone. And that's where people are getting in trouble. They don't recognize that. What happens as I increase this control head? Let's go to 40 feet. Now I went from 30 to 40. You see how the little blue line is shifting up to 40? So now it's zero flow. I've got to have 40 feet ahead. My minimum speed now is 67%. So you're beginning to see that this control curve, control head, fixed head controls the minimum speed of the pump and your brake horsepower savings. So you're not going to get that theoretical stuff that you thought you were going to get up front. We're going to get to the real world. Let's go to 50 feet. You see it 75% speed, 60 feet. I think you see it 83% speed. And let's go to 70 feet. And we're roughly 90% speed. Now remember, the slope of the pump curve is going to control this minimum speed. I got PowerPoint. I'm just showing you what's going to happen. So it's going to vary by the pump, whether you got a flat head pump, steep head pump curve, all those things. But the last one I got here is we now have 100% constant head, 0% variable head. It would be the same as if you took the differential pressure transducer and put it across a section and discharge tappings of the pump. Because then you got to set it for the full head of the pump or the worst condition, or everybody won't be happy. And then the minimum speed is 90% at zero flow, and you thought it was going to be zero? Look at the horsepower. Do you not begin to see why people are getting in trouble, not understanding this fixed head, control head thing has been a piece of your total pump head, and it's the one controlling? Simple statement here. It's worth you hanging on to. The only thing that would change your pump speed is variable head. The only thing will let you go to lower speeds is variable head. The constant head will not. That's what you kind of got to get through your head and begin to think about. So another question. What happens to this beep best efficiency pump? What happens to the efficiency of my pump at half flow? We just said we don't run 100% load, 100% flow all the time. Maybe only 1% of the time heating or cooling or with maxed out. We say we really live around 50% load, and we're going to assume around 50% flow majority of the time. So let's look at a little load profile. Let's take a look, not at 100%. Let's look at 50% flow and see what happens to my best efficiency pump selection, my efficiency, as I vary that constant head. Back to that constant head story again. So let's take a look. Same little pump curve we had earlier. So in this particular case, if I had, what would happen to my best efficiency pump efficiency as I change the amount of variable head versus constant head? Here we go. I got a pump curve at half flow. The actual total flow in this pump was 800 GPM at 110 feet ahead. Let's look at 400 GPM, which would be half flow where we would normally live. Let's see what happens as we change that control head percentage of the total pump head. Total pump head's 110 feet. If my control head was 0, I would have what? 100% variable head. Just about impossible to find. No two-way valve. What would happen to my beep? It's the purple line. Remember, we talked about it earlier. If I got 100% variable head, then at 0 flow, I go to 0 head. I follow the purple line. I follow the beep line of 85% all the way to 0. Only if I have 100% variable head. This one statement is getting lots of people in trouble because show me the job without a two-way valve. Show me the job without a two-way valve. Show me a job without any constant head, and I'll buy this. But it's hard to do. You're not going to show me that. It's just about impossible. So this is theoretical. It's not really happening. So we got to increase the control head to get to the real world. In this case, 100% variable head keeps my 85% beep, just as we talked about. Let's go to 20 feet. So now we got what? We got 20 feet constant head, 90% variable. See how the purple line went up to 20 feet at 0? So what are we saying? We're saying, okay, now we got to maintain 20 feet differential at 0 flow, where before we were at 0. But now we're 20 feet at 0 flow to make sure that critical two-way valve, that critical zone has all the flow it needs when everything goes down. So go a little bit further now. What happens to beep? See the purple line? So it looks to me like at beep now we're down to 77 points roughly. That's where the 400 GPM half flow is crossing the purple line. We're no longer following the 85% all the way down like we did before. We're not doing this now. We see what's happening. Let's see what happens at 30 feet. Let's go a little higher, 40 feet. Let's go to 40 feet. So now I got 40 feet, 70 feet would be variable head. 40 feet's constant. What happens to my beep efficiency? You see how the curve to the left, the purple control line is up to 40 feet. I'm at 72% beep. Keep moving with this. 60 feet constant head, 50 feet variable head. My best efficiency is now 67 points. Notice at 0 flow, I've got to have 60 feet. I got to have, about 70% speed to get there. Keep that in mind. This is the real world. Let's go to 80 feet. And you see it's 65%. To 100 feet, I'm about 62%. And you see how the purple line is going all the way up. And I think you're kind of getting the message now, hopefully, that constant head will not change your speed. The only thing will change that speed is variable head, and your beep efficiency is also going down as you increase the constant head. So what happens to pump efficiency? Constant flow when you overhead a pump. We'll see some of these same slides, just trying to make a point to you. We're seeing this issue lots of places. I've seen it in Chicago, I've seen it in Raleigh, I've seen it in LA, I've seen it all over the country. Because people are buying pumps and just thinking they can put a variable speed drive on it and fix all their problems. You cannot. You cannot do that. And this is where we're getting in trouble. So let's kind of get across to you what we're saying here. Back to that same pump curve I had earlier, 800 GPM, 110 feet ahead. Great, no big deal. Let's assume it's a condenser water pump where I want constant flow of 800 GPM and or a hot water or chill water system with two-way valves at full load, which only happens 1% of the time, but it will happen. In other words, let's look at full flow in this application, either in a variable flow system where you need 100% flow, which load profile says maybe 1% of the time, but I need 800 GPM. Let's just say I've got to have 800 GPM one way or the other, part of the time, all the time, I need 800 GPM. What happens if you've overheaded the pump? This is critical. We're seeing major engineering firms make this mistake. You cannot fix an overheaded pump with a variable speed drive and get full flow. You cannot fix an overheaded pump with a variable speed drive and get full flow and hold on to what you had. And it's going to vary by pump curves, but let's just give you an example. This case, you told me the head was 110 feet, 800 GPM. I asked you a question. What happens if I need 800 GPM? My actual pump head is only 70 feet. In other words, you've overheaded a lot, I'd agree, overheaded a lot. But if you're at 70 feet only the requirement and you need that much flow, look at the blue line. where is 70 feet ahead going to be? Well, your variable speed drive is going to slow you down to what? You're 100% speed at beep, but you don't need 110 feet ahead at full flow. Only need 70 feet. So the variable speed drive starts slowing down. 90% speed, 80% speed. But what happens where that last green line, the last curve, which is 75% beep, by the way, what happens at that point if you get below 80% pump speed, if you get below 70 feet ahead? It falls off the pump curve. The pump dies. The pump cavitates. You're in trouble. You've just messed up. You've got a big problem. And we're seeing this all over the place. How do you fix it? How do you fix it? You got to go throttle the pump discharge valve. You have to go throttle the pump discharge valve. Add some head to it above 70 feet and get it back up on the pump curve. If you added 40 feet to it, you get it back to beep. But what does the energy code tell you to do? You're not supposed to be throttling. And the owners are getting smarter. The owners are saying, how come my pump's throttle and there's a variable speed drive on it? I am getting owners every day asking questions that don't know why, but they know that the code says that you should have a pump that hasn't been throttled. Minimize throttle losses is the way the code is written. Minimize throttling losses. So they put a variable speed drive on there so they don't have to throttle anything, and the pump won't stay on the curve and cavitates. You got to go back and add a balancing valve to make sure it stays on the pump curve. They recognize that as being wrong, and that's where the big issue is. We got to spend more time on this one because this is huge. So here's where it falls off the curve, and you see the selection 800 GPM, 110 feet ahead. You kind of get the idea of, I hope you understand that a variable speed drive will not fix this problem. If you insist on overheading your pumps too much, if you insist on picking them to the right of beep, you do both of those things, a variable speed drive is not going to fix it. You're going to have to throttle that pump, get it back up on the curve, and you just broke the law. You just broke the energy code if you want to get right down to it. So let's move a little bit further with the system curve and hit you another little concept about areas of a system curve, which comes right out of ASHRAE, and talk a little bit about it. Here we see with a two-way valve, and you see a system curve. The red would be the system curve with all the valves wide open, everybody following the same procedure. Now look what would happen if we start changing conditions. That system curve moves around. In other words, as I close and open two-way valves in a big system, vary the flow, I'm varying the head, my system curve shifts around. See how it shifts between changing conditions between open and closing two-way valves. So my actual operating point on the pump curve is not fixed. It's going to be moving back and forth is the whole point. So we're going to talk a little bit more about this concept and how the system curves move back and forth. And as you move back and forth on a pump curve, you're not operating at beep, you're running through efficiency islands. You're looking at areas there that you're going to take a look at. So what's the pump selection guides from ASHRAE and HI? HI and ASHRAE both have some comments. Best practice, as you see from HI, which everybody belongs to, is pretty much around beep, and they would caution you to go a little left of beep. That's kind of what they tell you, and there's some reasons for it. You can dig a little deeper if you like. Just going to quote what HI does. Here's the best efficiency pump curve idea. This one's 83.5. Let's talk about efficiency islands real quick. We mentioned it. Everything in yellow there would have an efficiency island equal to 83 points or higher. Jumping on down to the green, everything in the green would have an efficiency island equal to what? 80% or higher. So the point would be nice if we could take that 80% green island and make it bigger, our electric bill would go down. That's simple. If we could take that green efficiency island, 80 points, and make it bigger, your electric bill would go down. That's simple. And this is what we're after. In other words, we're not going to run that 83.5% beep pump. Even if you picked your pump there, it's not going to run there. It may run there 1% of the time, but it's not going to run there. It's going to be moving back and forth. That's the whole issue. What does ASHRAE recommend? This is out of 2012 handbook. You can go check me out if you like. It's subject to change, but that's what's in there right now. They're basically saying what? You got the guideline there, and they're still preaching to the left of beep. The reason they're still preaching to the left of beep is possibly in the turbulent region. I got red might be important to you. If you know your pump head precisely and you're tight on it, you can go to right of beep, no big deal. But if you don't know that, or if you're gambling a little bit on it, or you're not sure it's right, or you're not sure it's going to be installed exactly the way you laid it out, then ASHRAE is still telling you go left of beep so you don't get in a turbulent area. We'll talk a little bit more about that as we go. So here's kind of a summation that Pleasance Company is going to make this statement to you. If you want to pick a pump to the right of beep, you make sure you got the right pump head loss calculation. You make sure it went in the way you designed it. You make sure you got the equipment you specified. You make sure you got the pressure drops that you originally picked on the equipment, and you don't have a lot of overhead. You haven't got a lot of safety factor. If you're not going to do that, pick to the left. To the right of beep, if everything's perfect, might give you slightly more efficiency as you cross these efficiency islands. It might give you a little bit higher if you don't fall off the curb because you're slightly overheaded. The key thing again is ASHRAE 90.1 2010 is telling you to do a detailed pump head loss calculation. But did you put a safety factor? How much? Are you overheading? Did you get the same equipment? Did the piping go in exactly the way you laid it out? Same number of T's, same number of elbows, same pipe size? Or did somebody change something? I can't answer those questions. You're going to have to answer them. But we're going to caution you because we see people getting in trouble. Way overheaded pumps, pick to the right. It's going to be trouble. And I don't know how we deal with that issue other than making sure you understand it. So here's again from 2012 ASHRAE handbook, and you see beep, and they're still steering you to pick slightly to the left when you can, simply because to stay out of turbulent areas. Because if you fall off that pump curve, the pumps get cavitated, you're going to tear them up. You're going to have to go back and throttle a valve to get it back on the curve. And what are you doing energy-wise now if you're throttling the valve? I mean, you just kill the whole thing. You can't really get away with it. So efficiency island, low profiles, I think you kind of get the message of where we're headed with this. But here we go. I got a system curve crossing over a pump curve, that little blue line. That's where it's going to run. Always, it's going to be at that point. First law of thermo, energy in, which is the pump curve, energy out, which is the system curve. Where they cross is going to be equal in energy, and you can't change that. You can't specify that on the drawing. That's what's going to happen in the real world. And that's where we got to look at the efficiency of the pump and see what's happening. So efficiency islands, we start looking at a little bit. What we're seeing is there's a lot of modern pumps out there, a lot of pump efficiencies out there, a lot of people trying, which is the right thing to be doing to improve the pump efficiency. Well, it's not all about just looking at that beep anymore. We need to look at that island a little bit, and we got to define an island. So here's an island for you, and I'll flip through several of these slides pretty quick. I think you already got the concept. We need to look more than just beep. There needs to be an envelope or some definition of an efficiency island, and we need to match it up to the real world of constant head, making sure the pump head loss calculations are correct to get the true operating cost of our pump. That's what we're after. So here's a definition. You see this particular one. I think everything inside of that is 81% efficiency or higher. Here's a little different picture on what it is, and you kind of see there's various ones you can have. You can pick the one. This is 81% as well. There's a little bigger picture of it. Still the same slide. 81% or higher in that efficiency island. In other words, if we could keep our system curve bouncing between those two lines on the island, we would never get below an efficiency of 81 points. And we cannot keep our pump at 86% beep all the time. It's impossible. Cannot be done. So what would be your goal? Obviously, if you were a pump designer building pumps, you want that island to be as wide and as deep as you can get. But it's going to vary by pump vendors. It's going to vary by models in the same pump line. Now, you can get individual pump you want to pick. There's going to be a bunch of different models you got to look at, decide which one is best based on your load profile. Based on your load profile, that's the key. So let's go back to this two-way valve idea, this shifting system curve. Try to bring these pieces together. So you see, we just talked about the efficiency island bit. Now we're back to the system curve, and you see how it's shifting back and forth. So you begin to get the idea, if my system curve is shifting back and forth with a system curve area, wouldn't it be nice to make sure that area, as we've shown in the slide, has the highest overall average efficiency we can get? And that's where we think we got to go with modern pump selections. Kind of drive the point home to you a little bit further. Here's a direct return system. I've got a pump, and you can see I got 6 zones, two-way valves, 600 GPM total. Now, there are many different system curve areas here, many different places to shift at part load. Now, if everything's wide open, all the two-way valves are wide open at 600 GPM, 1% of the time, we know where we are. But anything less than that, do you know what your system curve is doing? Do you know really where you are? Let me give you an example. Let's assume that our load is down to on 100 GPM, okay, just to keep it simple. This is direct return. Do you know which zone needs the 100 GPM? Is it zone 1 at the top or zone 6 at the bottom, or maybe a little bit of flow to all of them? We don't know. We just don't know. But wait a minute. What happens to the required pump head? This is critical that you understand this. What happens to the required pump head at 100 GPM if it's direct return? Wouldn't it be practical to say to you that if zone 6, the one closest to the pump, needs 100 GPM, and all the other two-way valves are closed, that the required head is minimum, low, compared to zone 1? Go to zone 1, taking 100 GPM, and all the other zones are closed. You see, it's the furthest one away. It's direct return. It's going to take more pump head to pump the same flow rate of 100 GPM through zone 1 than it does to pump it through zone 6. In other words, when you see a band of 100 GPM, you don't know the head. It could be zone 1, which is going to be the highest head requirement, or it could be zone 6, which would be the lowest head requirement. Those two-way valves closest to the pump need less head than those two-way valves furthest from the pump. It's called a direct return system, one we've been dealing with for years. Now let's plot that and see what that means. So what we're telling you, system curves have many paths and many areas that we got to deal with as the two-way valves move back and forth. Let's take this and let's plot it on a curve here for you so you can see. Here's a plot, and you almost just real. I got just some ASHRAE. This is right out of ASHRAE Figure 13, Handbook 2012, and ASHRAE calls it a control area. It's not my definition. This is ASHRAE's definition. So backing up, I just color-coded the slide I just gave you to make the point. If we calculate a system curve, we would think it would be the red line. That red line is true at 2 points: 0 flow, 100% flow. See where they come together? Otherwise, you don't know where you are. In other words, the lower blue line would be the two-way valves closest to the pump. The higher blue line would be the two-way valves furthest from the pump. The control head in this case is 20 feet at shutoff. But here's a message again. Let's assume I need 3,000 GPM. What pump head do I need? What pump speed do I need? I'm at 3,000 GPM. What pump head do I need? If the two-way valves closest to the pump are open, then I need what, about 25 feet. If the two-way valves furthest from the pump are asking for the 3,000 GPM, and I don't know, how much head do I need? I'm just roughly would need what, about 55 feet. So you could be at 3,000 GPM, you can be anywhere between 25 feet and 55 feet head requirements on this pump. You can be anywhere between those two numbers, and you have to have the pump speed to get you there, horsepower to get you there. You're beginning to see why you cannot use just one fixed control curve. You need to be able to change the differential. That red line is great, but that red line is going to get you in trouble if the two-way valve's further out. You're going to be short of flow. If that red line is your control point and you're close to the pump, you're going to be over pumping. So you're not going to be as efficient, and you're going to be in trouble if you try to put one constant differential head in there. That's the message. We're going to build on that in a future seminar, but that's critical. You begin to understand the control area and the fact that if you happen to pump through zone 1 furthest away, same GPM, takes more head than zone 6 closest to the pump. That's critical. You begin to think about that one. We're going to come back to that in a future seminar. Here's the control area we just talked about. So this efficiency island thing we talk about a lot. I think we already kind of defined it. Width, difference, and it's just kind of more definitions of it and why we want it. And again, I have now taken this control area from ASHRAE with my two-way valves, and I plotted it. Guess what we're going to do next? We're going to put it on a pump curve. Here's a control area. Here's a control area from ASHRAE. ASHRAE handbook calls it a control area. I repeat to you, at set flow rate, you don't know what head you need. Again, 300 GPM, I would need, what, about 25 feet ahead or 55 feet ahead? Depends on where I am. I don't know where I am. I do not know. I got to be satisfied those conditions. So let's take that and throw it on, put it on a pump curve. So all I've done right now, I've taken my control area and I popped it onto a pump curve. You see it's picked at beep is, about 600 GPM, slightly to the left of beep. Beep is 85 points. I can also take it and go slightly to the right of beep. All I've done now, I've taken that same control area and put it slightly to the right of beep versus slightly to the left of beep. Slightly to the right of beep, you could argue that my control area is going to cross efficiency lines a little bit higher, and my over average efficiency might be better. That's true. I'm not going to disagree with that. But ASHRAE is going to still tell you to pick it to the left of beep unless you do a detailed pump head loss calculation. We are too. So here's the message. Can I pick it to the right of beep and maybe pick up a pump efficiency a touch? Yes, I can. But I'm living dangerously, and you best be sure you got the right pump head. You best be sure you got the right pump head. And that's the issue. You got to make that decision. We would not argue with you at all that it might be slightly higher if you do a good pump head loss calculation. If you don't, you may fall off the pump curve. You don't have much safety. You're losing your safety factors. So in a modern pump design, we're able to control these areas a little bit. We're making them bigger. And I want to get back to this load profile and bring this together for you where we want to go. What we're after is we think we should begin to look at maybe an IPLV-based load profile and do a pump efficiency based not only at beep, which is 1% of the time, but look at 75%, 50%, and 25%, and load that efficiency in, weight that efficiency based on percentages in IPLV, because that's going to give you a much truer picture of what's going on in your system. We would suggest this pump spec to you, and by the way, we're going to drop to a 40% fixed head, 40% fixed head, 40% constant head, 40% of your total pump is required for the control valve, 6% would be variable. We're going to default to 40 unless you know the actual number. Be much more accurate if you know your actual number, but if you don't, we got to have a number to go to, and please don't put 0 there. Please don't put 0% fixed head. You're going to get in trouble. You're going to take that and promise it to the owner, and you're not going to get the savings. In the real world, if we have to average things out, we're okay saying that 40% is probably a good average, that 40% of the total pump head is fixed or control head most of the time. 6% is variable. So we're going to default to that unless you tell us your actual number, which we would prefer. But it's not 0. And you got a lot of pump vendors, a lot of variable speed drive preaching it's 0. It's just not true. People are getting in trouble. Please don't go down that road and get yourself or your firm in trouble with a 0. That's why we're pushing this so hard. We're trying to help you out a little bit. To go a little bit further with this, right back to the pump efficiency thing, we're going to say you be at that efficiency 1% of the time, 1% for 100% flow, 50% 45. We're just going to weight the efficiencies. In other words, we're going to look at the pump efficiencies at each one of these flow rates, and we're going to take that efficiency and weight it to get a blended efficiency. Very basic, simple idea based on an ARI load profile from IPLV. Based on an ARI load profile. What could be wrong with that? Everybody already understands the load profile. If you got your own load profile, load that in. If you don't, then let's use the standard load profile that every pump vendor can get a hold of. Everybody understands, and we can use their coordinate to get the highest system pumping efficiency, to get the lowest kW electric bill. Make these islands as big as you can. So as you shift back and forth, you keep that average weighted efficiency higher. So here's an example and kind of summarizing it for you. You want big efficiency islands, not little ones. The bigger the island, the lower your electric bill is going to be. Here's a quick example on overheading. Don't overhead pumps. This is the biggest mistake we're seeing made. I want everybody to kind of quickly review in their mind what I'm talking about. Here's a guy just overheading pumps like crazy. He doesn't understand it. Why? Here's a little pump curve to give you the concept again. Here we go. I've got a situation here where the control head is 35 feet. In other words, the minimum head I need is 35 feet. At full flow, at that 1% of the time that I've got a full flow requirement and or maybe a condenser water pump, either one, I've got to have full flow 2,000 GPM. I got my pump picked for about 95 feet ahead. Now, what happens if you've overheaded the pump? You've got to follow that vertical line straight down, and you see down at below 50 feet, I've done a 1380 RPM. In other words, as I slow the pump down with a variable speed drive, I'm following that straight line down, but I got to keep my 2,000 GPM. Sooner or later, you're going to fall off the pump curve. Depending on how bad you did it, how much you overheaded, I can't control. I just want you to get the concept. As a variable speed drive changes speed, that pump curve collapses a little bit. The max run out comes down. In other words, the max run out at full speed was, 2,600 GPM. The max run out at 1380 RPM is 2000 GPM. So depending upon how far to the right you went a beep, depending upon how much you overheaded the pump, you may be in trouble. You may not, but you may be. You've got to start understanding this concept, because in any system, you're going to need 100% flow sometime. Maybe only 1% of the time, but you're going to need it. And when you need it, you want the pump to run there. And if you messed it up by having overheaded, you're going to have to go back and add a throttling valve to keep it on the pump curve, and people don't like that. A little bit further, there's a concept on variable volume savings. Here is a pump selection based on, we're going to use IPLV low profile to kind of give you a little point here as we close this out. 100% variable head. I said it was about impossible. Let's look at this pump. The beep on this pump is 89 points. That's a pretty daggum good pump. 89% beep pump efficiency. If I had 100% variable head, that curve's going to track all the way down to 0. See that back to the left-hand curve? It's at 0 flow, 0 ed, 0 speed, 0 horsepower. We said it's impossible, but this is what would happen, and we would stay on that max beep efficiency all the way down. We would hold it. Let's put a low profile on it. I put an X on this because I don't want you using this one, because this is 100% variable head. We know you're not going to get this, but we took the IPLV low profile and put it on this pump, and we picked the efficiencies. We weighted the efficiencies per ARI IPLV low profile, and you see what happened to pump efficiency when my real red line is. It stays at 89 points, 88.5 all the way. Look at the brake horsepower. It went down in 0.98 at 25% load. Look at the RPM down to 466. We loaded in 10 cents a kW, low profile we just talked about, and you just went to the owner and we said to the owner, your annual operating cost with this variable speed drive is going to be $10,000. $10,000 is going to be your cost. Here's proof. Here's the load profile. Is what you're going to get. We even went to the right-hand side and plugged in the wire-to-water efficiency for the motor and variable speed drive. We all know that's wrong, but that's what was promised to the owner. We know that's wrong because you're going to need two-way valves. Let's go back and add a two-way valve. Same pump, same load profile. I'm going to say I need 30 feet of constant head. I'm going to have 30 feet of constant head out of my total. And you see back at 0 flow, my control curve goes to 30 feet. Back at 0 flow, my control head goes 30 feet. This is more like the real world. Let's go back and put that same load profile back on it as before. I got 30 feet of constant head now. Let's take IPLV and see what's happened to my operating costs. First thing is look at that pump efficiency at 25% load. At 25% load, 25% flow, my pump efficiency dropped from 89 points, 88.5, to 68 points. Look at my horsepower. My horsepower before was less than 1. Now it's 6.32. Most importantly, what was the electric bill to your client? You promised him $10,000. What is the electric bill? $14,500. Who is going to go to that owner and client and give them a check for $4,500? That's what is upsetting people, and the owners are catching on. We've got to begin to look at the real world. That's why we say to you, let's use some fixed head, don't assume 100% constant, and let's start looking at our load profile like IPLV because it makes a lot of sense.